Welcome to Sundar's lecture. This is lecture number 17, and in this lecture we are going to start a new topic, that is combinational logic circuit with the basics of Karnaugh web and whatever we have seen in our previous classes, right? Before that, I have left one topic. See, we will see that. See, what are the topics we have seen anyhow in the previous class? We have started with the universal gates, right? So, which are all the combinations of universal gate or a particular gate called as a universal gate, and we have proved that NAND gate and NOR gate can be considered as a universal gate, right? So, and then we have came to this implementation of Boolean expression with logic gates, right? So we have just implemented this Boolean expression. This is actually SOP function, right? So we have implemented with logic gates, and we have also implemented the same expression with only NAND, right? So we have seen this one, and let me do this one now. Implement the Boolean expression with only NOR gates, right? So what you do now, you generally go for if they have given you any expression like this, you generally go for normal gates. You implement with the normal gates, and then you convert that normal gates into NOR gates, right? So what you do now, so this is an POS function, right? Obviously you know this is a POS, right? So product of sum. So what you need to do, you have AND gates, right? In between you have multiplication. So what you do, simply you put a AND gate, right? This is AND gate. Anyway, I will take less time because we need to start a new topic, right? So this is an AND gate. How many inputs are there? There are 3 inputs. 1, this is 2, and this is 3. Simply. And what is the input you need to give here? This is the first input, so it will be A plus B bar, right? So this will be A plus B bar, and second one will be A plus C bar, and third one will be A bar plus B plus C, right? So now this is Y, right? So anyhow, this is an expression called Y is equal to, right? So now this is Y, right? So I need to put R gate now to implement this one. What I need to do, I have to put the R gate. So to use this one, I will put an OR gate. So this one can be connected like this, and another OR gate, another OR gate. What I need to do, I have to connect this one here, and I have to put another OR gate, right? This OR gate. So what I need to do, I can connect these two, right? So this is how you need to connect this one. So what is the input? There are 2 inputs for this and 2 inputs for this, but this has 3 input, right? So 1, 2, 3, and you have to write the inputs now. This is A, this is B bar, and this is A, this is C bar, this is A bar, this is maybe I have to write like this. This is A bar, this is B, this is C, and you already have what? You already have A, B, and then C, right? These 3 you already have with you, and you need to connect everything right now. So you have to connect this one with A, and if it is B bar, then what you need to do, put an NOT gate and you connect like this, and from A you connect this one now straight away, right? This one, and for C bar you connect like this, right? I am taking much time. Anyhow, A bar, I need to go again to put this one now. This is A bar, B, and then this is C, right? So anyhow, this to be connected like this. So this is now the connection, right? So this we have implemented this particular expression with the gates. Now what you need to do, you have to implement only with NOR gates. That is the principle, right? So what you do now, I have already told you. Anyhow, we have already done this. You make this as a NOT. Maybe I will use a different dark colors. So this as a NOT now, and put NOT here. Both are same, right? I've already told. So put a NOT here, put a NOT, put a NOT here. Simply. And what is this one now? What is this one? We know, right? What is this one? What is this one? This is inverted input and gate, which is nothing but we can call it as what? NOR gate. We have seen, right? Inverted input and gate, right? Inverted input and gate. See here, inverted input and gate. What is that? It is an OR gate. I have already told you, right? So what you can do now? You can just replace this one with an OR gate, right? So I will rough it out, and anyhow I will take it to the next page to draw this one, right? Right. What I can do now? I can just rough this one right away. Rough this one. What I can do now? I can just put an OR gate simply, because we have proved this one, right? We have proved this one. So this is now. So you can connect this one, and then this one. So now you see this is an OR gate, this is NOR gate, NOR gate, NOR gate. And what I need to do, I have to wrap it out this one. So what is the principle of this one? How you can put the NOR gate using NOR gate? Simply you short circuit the inputs of the NOR gate, right? You can draw like this. And for this one too, what you can do, simply short circuited input NOR gate can be considered as what? Not gate, right? That is also we approved already. That is also we approved. So now this one you can connect like this, and you can draw like this, right? So now you look into this circuit. It is very simple. Everything is an OR gate. So we can implement like this. This is also a correct answer. Uh, if they have given you only using logic gates, they have not mentioned you to draw the circuit only within NOR gates, then you can draw this one. If they are asking you to draw with NOR gates, do draw this diagram and then convert it, right? So this is the whole idea. Right, now you come to this one now. This is a new topic, that is combinational logic circuits, right? What is combinational logic circuit? It has set of inputs and outputs, right? It has set of inputs and outputs. It is a group of logic gates connected together to perform a certain operation. And what is this one now? See, generally what we will have like this. A box will be like this, right? It has set of inputs. It has set of inputs, maybe 2 or 3 or 4, or it may be have set of outputs, 1 or 2 or 3 outputs, whatever it may be, right? So this is now, we generally call it as combinational logic circuit. Combinational logic circuit, right? So this is now A, B, C, D, and this one can be Y1, Y2. And what is this combinational logic circuit now? It is a connection of logic gates. Logic gates will be connected to perform a certain operation. See, we will take an example now, right? Right, I will just write down that question and I will read it out. Right. Now you look into this question now. Implement a logic circuit for 3 inputs where the output is high when 2 inputs are high. Can you understand what is the question now? It is a 3 input system and the output is high only when 2 inputs are high, right? That is the condition they have given you. See this one now. This is the 3 input system. I have just written the 8 number of combinations, right? So you compare this one now. You see the inputs. All the inputs are low, so it will be 0. See here only one input is high, right? So it is also 0, because when the given question is when 2 inputs are high, right? This is also 0. And you see this one now. 2 inputs are high, right? B and C. So the output will be 1. And you see this is only one input is high, so it will be 0. And you see this one, 2 inputs are high, so it will be 1. 2 inputs are high, so it will be 1. Again you see there are 3 inputs are high. What is the question they have given you? 2 inputs are high, right? So you can put this also. Right, what is the min term for this one now? This is 0, 1, 2, 3, 4, and then 5. This is 6, this is 7. Right? Now what you can do, you can just simplify this equation using Karnaugh map, you will get an expression, right? Simplified expression. That is what we are going to do, right? Right? Right. Now I have taken like this, right? So this is 3 input system. So I have taken 3 variable kernel, right? So what you need to do, you have to put which min term is high now. 3 is 1. So this is 1. 4 is 0. 5, 6, 7 is 1, right? So 5 and then 6 and then 7. So all other terms, all other cells will have 0. And how will you map this one? So I will go fast because this one we have seen many a times, right? So you have to map these two. There is no quad possibility, right? So it is only pair possibility. So and these two as another pair. Maybe I will take a different color. So these two as another pair, and these two as another pair. So three pairs are there. So how will you write the expression now? Straight away you can write the y. So for this one, blue color, what you will have, this is a and then the common term is c. So ac is the first term plus what is the second term? Maybe we will take this one. Straight away it is bc, and then plus this one, it is a. What is the common term in these two? It is b. Right? This is b. So this is the final expression, right? So what you can do with this now? So you can draw the logic diagram using this expression now. This is a simplified version of expression, right? So what you do, you just take this one. Maybe I will take it to the next page so that we can draw the diagram, right? So I have taken this one. See here, there are three. This is SOP function, right? So you will have OR gates straight away. So I can draw the OR gate right now. So for this OR gate, how many inputs are there? So this is now OR gate, and this is Y. Y. This means this equation comes here, which means AC plus BC plus AB, right? This. So you have three inputs right now. You should have three inputs, right? So for this one, so 1, 2, and then 3. And what are all the values now? What are all the values? This is AC, and this is BC, and this is AB. That is the thing. And you have to draw for AC. This is very simple, right? So it will be a AND gate. So I will draw here. This is an AND gate, and again an AND gate. Three AND gate should be there, right? So again this is a AND gate, right? So this one can be connected like this, and this one can be connected like this, right? So now this is how we need to connect. And what should be the input for this one now? That is the thing. This is AC, right? AC, right? So where I need to get the input now? From A, one input should be from A, and one input from C. This one. And for this one, it is BC, right? So from B and then from C. There is no NOT gates are there because everything is a normal term, normal literals, right? So and then again it is A. So I need to take it from here, A, and then B, B. That's all. That's all. See here, what is this one actually? I will just put like this one up to this one. I can draw like this, like this. What is this one now? What is this one? This is nothing but combinational logic circuit. So what is actually here? This is output Y. This is the input ABC. It has set of inputs and set of output. Here we have only one output, and it is performing some operation. What is this performance? If you give three inputs, that means 000 or 001, whenever you have two inputs are high, the output becomes high. That operation is performed by this gates. This is nothing but we are calling it as combinational logic circuit. Can you understand? That is what we have seen as a definition, right? This is the combinational logic circuit. That is what we are having here, right? So what we will do now, I have just given you an example to understand, but the applications are very simple. First we will go for adders, right? Adders. What is adders? And I will just write it as half adders. Half adders. And what is half adders? It is 2-bit addition. 2-bit addition. That is the idea, right? What is 2-bit addition now? 2-bit addition in sense you have to write the truth table for this one. maybe I will write the truth table now. How will you write the truth table? This is A, this is B. And for adder, what will be the outputs? It will be sum, it will be carry, right? If you add any two numbers, what you will have? You will have some value and then you will have a carry, right? So this is how you need to write. So I will write it as sum and then carry, right? If it is a two input system, right, I will draw the tabular column. Right, now you look into this one. So if you add these two, what you will get? 0 plus 0. Obviously it is a 0, right? So sum is 0, the answer will be 0 and carry is also 0. There is no carry, right? So if you add 0 plus 1, now what will you have? This one is sum is 1 and I don't have carry, right? So it will be 0. 1 plus 0, again it is 1, the carry is 0. And 1 plus 1, what is the answer? See, it is a binary addition, not 2, right? 1 plus 1 will give you 10. So if you have 10, what will you do? So for example, if you add 25 with the 27 anyhow, so how will you add this one now? These two, if you add 12, so you put 2 in one, you have to put here, because what is this one and what is this one? This is nothing but we generally call it as sum, and this is nothing but we generally call it as carry, right? Can you understand? So that is the whole idea. And if I have 10 now, sum will be 0 and carry will be 1, right? If I have 1 plus 1, what I will have? 10 is the answer, right? So if this is sum, and this will be now carry, right? So this is how you need to write it down. So what you need to do now, you have to simplify this one. These two are the inputs, and this is one separate output, this is one separate output. What will you have now? So I can straight away give you the values, right? Anyhow, I will put the K map. Right, see here, anyhow, I don't need to draw this one. Anyhow, I just want to tell you how this one is really working. So for sum, this is the K map. For carry, this is the K map. So for this one, it is 0, 1, 1, 0, right? That is the thing for sum. For carry, it is 0, 0. This is 0 and this is now 1, right? So what you can do here, there is no pair possibility, right? Because you cannot do this one. So what you need to do, you have to separately map this one as separate one, this is separate one. And what I will have now for sum, I can write s is equal to, this is the first equation, a b bar, right? So this will be now a b bar plus this one will be a bar b, right? So a bar b, that is for sum. And for carry, what is the option? Only this one can be separately done. So this is AB, right? So this will be now AB. So this is the equation you are getting. What is this one actually? What is this one actually? A bar B plus AB bar, which is nothing but we have already seen this as A XOR of B. This is the idea. So how will you draw the diagram for this one now? For half adder, what is this one now? A and B are the inputs now. A and B are the inputs now. Anyhow, I will draw like this. A and B are the inputs. And what is the thing here? What is the thing here? You have an XOR gate. You have an XOR gate, and this will be here. So this input is connected to this one, this input is connected to this one. So what is the output now? This is now sum, that is nothing but it is A XOR of B. And what you need to do for carry? For carry, this is an AND gate, right? This is an AND gate, right? So this will be now like this. So put an AND gate, and you can take output as carry is equal to AB, and I can connect like this, right? So this input, this one, maybe AB can be done anything anyhow, right? So this will be now the diagram for half adder, right? If you give AB, so this one you put a box like this. So there are two inputs now, multiple inputs, multiple outputs, right? Two inputs, two outputs, right? So for this one, you will get the output as this equations, right? If you give 0 0, sum is 0, carry is 0. If you give 0 1, sum is 1, carry is 0. And if you give 1 0, sum is 1, carry is 0. If you give 1 1, sum is 0, carry is 1. This diagram will perform that operation, right? So this is now an half adder. Right, I don't need to draw this corner map, try to understand. See this equation now, it is 0, 1, 1, 0. Inverted inputs getting output as 1. What is this? This is XOR gate. So you can straight away put A XOR of B. And you see this one now, 0, 0, 0, 1. What is this output? What is this output? It is an AND gate, right? For an AND gate, you will have 0, 0, 0, 1. So obviously what you will have? This equation. That is the two things, right? You can straight away draw any. I want to tell you like this, right? So for XOR gate, you should have one simple understanding. See here, if you compare any two cells, compare these two, this is inverted. This is 0, this is 1. Compare these two, this is 0, this is 1. Compare these two, this is 1, this is 0. Compare these two, this is 1, this is 0. If you compare any cells, any adjacent cells, if you have inverted ones and 0, then the output will be XOR. Simply, the output will be XOR. This is the basic idea you have to understand. So this is now half adder, right? Now what we will do, we will go for the full adder now. Full adder, right? Now you see, you have to come fast now. So 0 plus 0, it is 0. Again 0 plus 0, it is 0. So sum will be 0. There is no carry, so it will be 0. And you see 0 plus 0, it is 0. 0 plus 1, it is 1. So sum will be 1, carry will be 0. 0 plus 1, it is 1. 1 plus 0, it is again 1. So 1 and then carry will be 0. See here, 0 plus 1, it is 1. 1 plus 1, it is 10 now. So 10 means sum is 0, carry is 1. And 1 plus 0, 1, and then it is also 1, right? So carry is 0. So 1 plus 0, it is 1, 1 plus 1, it is 10, right? So 10 means this is 0, this is 1. So 1 plus 1, 10, 10 plus 0, it is 0. So 10 means, so it is 0, this is 1. And 1 plus 1, it is 10, right? 10 plus 1, it is 11 now. What is 11 plus 1? It is 100. Try to understand binary value. So it will be 11. So carry is also, sorry, sum is also 1, carry is also 1. Now this is the equation for sum and the carry, right? So what you need to do now, you have to draw the schema separately for sum, separately for carry, right? Right, I have just drawn the diagram, Karnaugh map, right? So what you need to do, go for sum now. For 0, for 1 and 2, it is 1, right? So for 1 and 2, it is 1, and then for 4 and 7, 4 and then 7, all others will be 0, right? 0, 0, 0. And for carry, which is 1, 3 is 1, right? So this is 1, and 5, 6, 7. So 5, 6, 7, all others are 0, 0, 0. So what you see here, any kind of pair is possible here. No quad is possible, no pair is possible, right? Nothing will be possible here. So what you need to do, you have to take separately this one, this one, this one, and then this one. And I have told you one thing in the previous one, right? What we have seen here, if it is like this, then it is an XOR, right? So see here, this is different, this is a different, this is inverted, 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 everything is inverted here, right? Then obviously what will be the equation for this one? Sum. What will be the equation? So obviously it has to be A XOR of B XOR of C. It has to come like this, right? Anyhow, maybe I will write the equation for sum. Get the equation from here now. It is A B bar C. So it is A B bar C bar. That is for first one. For second one, it is A bar B bar C. It is A bar B bar C. Plus the third one, it is A B C. It is A B C. What is the fourth one? It is A bar B C bar. This is the equation, right? So what you can do now, you can just simplify the equation. So how will you simplify this equation now? What is the procedure? Take A as a common term, right? This one. This is A as a common term. In these two, A is a common term. Take A as a common term. What will you get? It is B bar C bar plus BC. That is one term. Take A bar as a common term in these two. A bar as a common term. So what will you get now? It is B bar C plus B C bar, right? So now it is very simple. What is this one now? What is this one? It is an XNOR gate, right? So this is nothing but it is an B XNOR of C. Just check it out my previous lecture to understand this one, right? So this is XNOR and then put plus A bar, and what is this one? It is B XOR of C, B bar C plus B C bar, right? So it will be B XOR of C. So again, what is this one now? This one can be written as like A B XOR of C the whole bar. I have already told you, right? So this one now will be B XOR of C. So what this whole expression looks like now? What this whole expression looks like? Try to understand me. Try to understand very clearly. You keep this as now B. B XOR of C consider as B now. So A B bar plus A bar B. Then what will be the expression? So A XOR of, what is B here? We have considered it is B XOR of C. So it is B XOR of C. Simply we can write like this, right? So the output equation, I have told you, right? It has to be like this, right? So what will be this one now? You have to separately do, no. What we need to do? We have to pair this one, right? So this is a pair, and this is a pair, and this is a pair. These three are the pair. So how will you write the expression now? Straight away you can write for carry. What is carry now? So it is A, and if you compare these two, what is the term? C. That is the two equation. Plus, and for this one it is A, B. It is A, B. Plus, and for this one it is B, C. It is B, C. Right? So now this is the expression for carry. This is the expression for carry, and this is the expression for sum. Am I right or wrong? So these two we have to draw the diagram, logic diagram. So how will you draw this one? Right. Now you see this one. This is the sum and carry equation, right? So what I can do now, I can put an XOR gate like this, and I can write this as my sum now. So where should I get this one? From A, I can draw this one. From B, there is a straight one from B, and I can go from C, right? Now what will be this one? What will be this one? So this will be A XOR of B XOR of C. So see, this one is sum. This one is sum. For carry, what you need to do? So see, you have to put an OR gate, like this, right? So you have to draw three AND gates, right? So three AND gates, and I have told you these type of things we have already seen many a times. So this is now, and three OR gates, right? So this one you can straight away give this one has to come like this, and this one has to come like this. So what should be the input of this one now? This should be AB, and this should be AC, and this should be BC, right? So I can give straight away right now. What I can do, I can connect from A to this one, and from B I can connect like this, and from A again I can connect to this one, and from C I have to take from here, and then I have to give it to here, and from B I can take from here, and this one can be connected, and from C I can take from here, and I can connect this one. So what is this one now? This is now carry, and what is the expression? This is AB plus AC plus BC. So now you see, you just draw a box like this, and you can see inside this combinational logic circuit I have these gates which can perform the 3-bit addition. That is how you need to understand. So what are all the topics we have seen in this class? See, we have started this class with the combinational logic circuits. So what is combinational logic circuits? It will have set of inputs and set of outputs, and that is going to perform this combinational logic circuit is going to perform some operation, right? So what is that operation? I have given a simple example. When two inputs are high, the output should be high, and we have just drawn the truth table, and we have drawn the Karnaugh map to simplify the equation, and finally we have drawn the diagram, right? Logic diagram. Now I have told you this is set of input, this is output, and in between this one, this is the combination logic circuit, and we have gone for half adders and then full adders, right? So we will see in the next class.